The position of a particle relative to the origin O is given by S of t is t cubed minus 9t squared plus 24t plus 2 meters. Find the expression for the particle's velocity and acceleration and draw sign diagrams for them. So first of all, we need to remember that velocity is the derivative, velocity is the derivative of displacement. So we take the derivative and we get 3t squared minus 18t plus 24. To do the sign diagram, we need to know the zeros, so we factorise, take out the common factor of 3 first, and then factorise the quadratic that's left. And you can see that we've got zeros at 2 and 4, which is where we get the 2 and the 4 from. The quadratic, the coefficient on the t squared is positive 3, so that means we've got a happy graph. So our sign diagram is going to be positive, negative, positive, and we need to be careful to label the velocity of, that it's the sign diagram for the velocity. With the acceleration, we need to recognize the acceleration is the derivative of the velocity. So all we've done is take the derivative of this equation up here, and it's 6t minus 18 meters per second squared. And to find the zero, we can factorise. So we'll get 6 outside of t minus 3. And so therefore, t equals 3 is a 0. So here's t equals 3. And the 6 on the 6t tells us that it's a straight line graph that is going to be positive, sloping upwards. So that's going to be 3. So the graph is going to be negative and then positive. And notice the inclusion of A of t. It's extremely important that you label your sign diagrams because there's multiple sign diagrams and we need to know which one is which. Notice the inclusion of this little block here. Okay, so the way that you would draw that if you were just drawing this is just a straight line with dashed on the back of it, and that indicates that the function doesn't exist back there. And the reason that it doesn't exist is because that would mean time is a negative, and because time is a measurable quantity, it can't be negative. So that's how you would draw that in your page. All right, the next question says find the initial conditions. So a reminder, all the way back up here, initial conditions means let t equal 0. So we do that for each of our 3 quantities. We find our displacement when t is 0, our velocity when t is 0, and our acceleration when t is 0. And we use the equations that we have discovered up here for velocity and acceleration. When we substitute in t equals 0, we get displacement of 2 meters, velocity 24 meters per second, and acceleration negative 18 meters per second squared. We do, however, have to describe the motion. And so what we do is we use those 3 pieces of information. So the displacement tells us that the particle is 2 meters to the right of the origin. It is moving to the right at a speed of 24 meters per second. That's what the positive velocity tells us. And it is accelerating at a rate of minus 18 meters per second squared. Now, we like to say decelerating, but in actual fact, we need to say that it is accelerating with a negative acceleration. That's the technically correct way to express it. All right, question C says describe the motion of the particle at t equals 3 seconds. So similarly, we find the displacement when t is 3, the velocity when t is 3, and acceleration when t is 3, which is 20 meters minus 3 meters per second and 0 meters per second squared. So at 3 seconds, the particle is 20 meters to the right of the origin because displacement is positive 20. It's moving to the left at a speed of 3 meters per second because velocity is negative 3, and it is neither accelerating nor decelerating because the acceleration is 0 meters per second squared. So it could be that the particle has stopped. It could be that the particle is changing direction at that point. And in actual fact, we assume that it is changing direction. All right, find the position of the particle when it changes direction. So to do that, we need to recognize that the particle's velocity is instantaneously equal to 0 when it changes direction. Because remember, it goes in one direction and then switches and comes back in the other. It doesn't actually curve around, but that's how we draw it. So it's just zipping forwards and backwards, forwards and backwards. So the way that we do that is we set our velocity equal to 0 and solve for t. We actually work that out up here in our sign diagram, that the velocity has zeros when t equals 2 and 4. So because we've already done that, we don't need to recalculate it, but we're calculating the position of the particle. So we find the displacement when t is 2 and the displacement when t is 4. So subbing in t is 2, t is 4, we get 22 and 18 meters. So the particle is 22 meters to the right of the origin when it changes direction the first time, and 18 meters to the right of the origin when it changes direction the second time. All right, the next question says, draw a motion diagram for the particle. Now, on the previous lesson, the motion diagram that we drew really just looked like a number line. We have to do it's a little bit more complicated on this one because the particle is changing directions and we need to keep track of exactly where the particle is at what point. So we end up drawing what looks like a squiggle or an S, but in actual fact, the particle is still just zipping forwards and backwards. All right, we mark on here all of our critical information. So the first thing that we mark is that S of 0 is 2 meters. We put t equals 0 to indicate that the particle is at this point when t equals 0, and you must include that t equals 0. We know from this piece of information here that the particle changes directions for the first time when at t equals 2 seconds and it's at 22. So that's where this point comes from. T equals 2 seconds, the particle is at 22 units to the right of the origin and changing directions. We know from this piece of information here that when S equals 3, the particle is at 20 meters. And so we put a dot showing that the particle is at 20 when t equals 3. Again, notice the inclusion of t equals 0, t equals 2, t equals 3, and so on. We know from this piece of information that the particle changes direction again when it is 18 meters to the right of the origin. So here's 18. And we've got t equals 4 marked to show that it's changing direction. After that, we don't have any information. We know that the particle doesn't change direction again, so it's valid to assume that the particle just keeps on travelling to the right for the rest of its existence. There's no more changes in direction, so it just keeps travelling in the direction that it's ended up in. The only other thing to include are little arrows here to show that the particle, now that one's not super clear, that shows that what direction the particle is actually travelling in at that point on the diagram. You could even put one out here to indicate that it's travelling to the right. All right, question F says, for what time period is the particle's speed increasing? Remember that the particle speed is increasing when velocity and acceleration have the same sign. So basically what we do is we go back to the sign diagrams that we did up here and check where they've got the same sign. We've got a couple of critical points and we can line them up to work out which sections have the same sign. You can see here between 2 and 3 that both signs are negative. And you can see here when t is greater than 4 that both signs are positive. So it's in those regions that the speed is going to be increasing. So if we go and have a look back at the question, how we answer it. Now this says the particle is accelerating, oops, but it should say the particle's speed is increasing. So can you change that, please? So the particle's speed increases when the velocity and acceleration have the same sign. So we can see from those sign diagrams we just looked at that velocity and acceleration are both negative between 2 and 3, and they're both positive but for t greater than 4. So the particle's speed is increasing for those two regions, and you just list them like that. Notice that we do not include the endpoints. All right, so we don't write greater than or less than or equal to, it's only less than. All right, last question. What's the total distance traveled in the first 5 seconds? All right, going back to have a look at our diagram, we don't have any information about the particle's displacement at 5 seconds, so we need to calculate that. And in actual fact, what we find is that at t equals 5, our particle is back at 22, which is where it was at t equals 2, just by coincidence. And the distance that's traveled is literally found by adding up each section of the motion diagram. So this first section, it goes from 2 to 22, so that's 20 units or 20 meters. This second section goes from 22 back to 18, so that's 4 units. And then this third section goes from 18 up to 22, so that's another 4 units. And so that's where the 20 plus 4 plus 4 comes from. Add them all together, and the particle has travelled 28 meters. Okay, that's it. That's enough to get you going on exercise 15E.2.